When we think about electrophilic aromatic substitution reactions, we have to remember that because this is an electrophilic process, benzene is a nucleophile. And as a result, things that make it more nucleophilic will increase its rate of reaction, or its reactivity. By contrast, though, things that withdraw electron density, that make it a weaker nucleophile, will make it deactivated towards electrophilic aromatic substitution. And so this ties into the directors that we looked at last time. We're going to see that activating groups will be ones that donate electron density into the benzene ring, allowing it to be more nucleophilic. And we see that the electron density will be pooled at the ortho and para positions, as we will see through resonance. So if we take a look at one of our absolute favorite, perhaps the most reactive of all the benzene derivatives towards EAS is aniline. When we look at aniline, it has a lone pair on the nitrogen, and that lone pair is free to resonate. And when it does so, we can resonate in multiple ways, and I'm going to try and just draw them all at once. So we have option one where we put the blue arrows, we're going to put electron density onto that ortho position on the right. That's option one. If we do the same thing with purple arrows, we can put the electron density at the para position. Or if we take a look at, how about these teal ones, if we go ahead and, oh my goodness, what a mess. We're going to end up with electron density on that other para position. So through this disaster of a resonance structure, with 3 different resonances happening, we see overall that we're going to have slight negatives at the ortho and para positions, just depending on the resonance, right? The resonance will push full lone pairs to those positions, which can then react, right? So those 3 positions are slightly negative overall through the resonance. And as a result, again, I'm going to put our double bonds as kind of a ring here. As a result, those positions are going to be the nucleophiles, the ones that are going to attack the electrophile, sorry. So remember, benzene is our nucleophile, so an electron donating group like an amine will push electron density into the ring to those 3 positions, allowing for those 3 positions to then attack an electrophile. So remember, electron density means it's easier to attack our electrophile, and I'm just going to put electrophile as E+. Since electrophiles are generally positively charged, it's easier to attack that electrophile. And so, if we want to think about that, we can classify our activators. We're going to see that we have strong activators towards EAS. All of these are in reference to electrophilic aromatic substitution. Strong activators would be amines, alcohols, alkoxides, various substituted amines. Let me just put this on R2. That's good enough. What we see with all of these, though, the important part is that all of these activating groups, the strong activators, remember AR is for aryl, that means a benzene ring. When these things are on benzene, they activate it very strongly. So much so that if you take aniline and try and brominate it, first off, you do not need the Lewis acid. It's going to go by itself. Secondly, you're going to try brominate it. You're going to end up putting a bromine at all 3 positions, both orthos and the para position. All 3 will be attacked, or will attack a bromine. So these things are very strong. They make your benzene very reactive towards electrophilic aromatic substitution. And notice all of these have a lone pair that is fully able to resonate into the benzene. So all of these, there's no other resonance happening here. They all have the capacity to fully donate in. So all strong activators and I'll abbreviate them SA, strong activators, SAs, have a lone pair they can delocalize into the ring. And so we'll classify these as strong activators because they can completely donate electron density. We're going to see we have other electron donating groups that are not as strong, and we call these moderate activators. The moderate activators, or MAs as we'll call them, would be things that have lone pairs, but those lone pairs are tied up. Either they're doing resonance into other things, so like an ester, for example, or they are alkoxides. Alkoxides technically have lone pairs that are able to resonate into the ring, but we see experimentally those typically are less activating than alcohol would be. So we are going to classify them as moderate activators. So with that in mind, we're going to see that ethers, so alkoxy groups, not alkoxides. Alkoxides, the negative oxygen, very, very strong activator. However, an alkoxy group, an ether, is a moderate activator. So the oxygen lone pairs can resonate into the ring, but they kind of just, they're not as movable as they would be with an alcohol. We see things like esters, where it's the oxygen side of the ester. Same thing with an amide. Amides are moderate activators. So we see here that we have these lone pairs, right? The lone pairs on this oxygen could resonate into the ring. They could resonate that way. But they're also resonating into the carbonyl. So those lone pairs are already tied up in other resonance. And so we see that esters and amides will be moderate activators because they are already kind of tied up. So they're already being used for resonance elsewhere. So they're not as free. And then if we go ahead and take a look at other ones, we're going to see that we have our weak activators. I'm not going to put a line. Weak activators, which we will abbreviate WAs. These are alkyl groups. So methyl groups, ethyl groups, isopropyl groups, T-butyl groups, whatever it may be. Alkyl groups are weak activators. So these only donate electron density through hyperconjugation, and that's a very weak effect. And so we see here that the moderate activators have lone pairs that are otherwise resonating. So they resonate outside the ring as well as inside the ring. So they're caught between two areas of resonance. Alkyl groups have no resonance. They stabilize only through, or they activate only through hyperconjugation. And that's a very weak effect, right? We saw that, having an allylic species, something that can resonate, is a lot more stabilizing than hyperconjugation is. A primary allylic carbocation is much more stable than a tertiary non-allylic carbocation. So hyperconjugation is a much weaker effect. And so we see that all of these activators are ortho-para-directors because they're all going to help stabilize either the sigma complex or they're going to donate electron density to help make positions more nucleophilic. So all activators are ortho-para-directors. And I'll just write ortho/para, just so we remember. That's what OP stands for. Not overpowered in this case, but they are ortho-para-directors. So, with that, we can now look at things that deactivate the benzene. And we're going to see that we have weak deactivators. which we will abbreviate WD, weak deactivators. These will be our halogens. Our bromine, chlorine, fluorine, iodine, all of these halogens are weak deactivators. So these withdraw electron density a little bit through inductive effects, right? That said, they are capable of resonating into the ring. So while they are inductively pulling electron density, so they are deactivating the benzene, making it less nucleophilic, they are still stabilizing the ortho and para positions. So if we see here a chlorine can still technically resonate its electron density to a para position or an ortho position if you want to draw the rest of them out. So we do see that they still donate some electron density to the ortho and para positions. So they are still ortho-para directors, but they are actually deactivating overall towards the ring because they are so inductive. So we do see that even though they are capable of resonance, typically they still deactivate the ring. They make it less reactive overall. And so they are still, so halogens are ortho-para directors. So even though they are deactivating, they are still ortho-para directors because they can resonate. We're going to see our other two categories, our moderate deactivators and our strong deactivators, are all going to be meta-directors because they can't resonate into the ring. They can only withdraw. So let's take a look at our moderate deactivators here. Those are our MDs. We're going to see all of the carbonyls. We have our esters, we have acids, we have ketones, we have aldehydes. Let's see, what else do we have? We have, those are all the oxygen ones. We can have some amides there as well. All of these will deactivate your ring. So notice all of these have carbonyls essentially that are going to help deactivate the ring. We also see nitriles under this category and sulfonic acids. These all will withdraw electron density. There's no way they can push electron density to ortho-para positions. They only withdraw, so they deactivate your ring. And we see that again, no resonance, so they're going to be favoring the meta positions because those will be the least unstable. So we're going to see that all of our moderate deactivators and our strong deactivators are meta directors, but we'll see that in just a second. Let's look at our strong deactivators. And those will be our SDs. So we have SAs, strong activators, moderate activators, weak deactivators, moderate deactivators, strong deactivators. So in that order, most activating to least activating. Least activating meaning the most deactivating will be our strong deactivators. And these will be our nitro group. Nitro is a strong deactivator, very electron withdrawing. We see, generally speaking, a trihalocarbon, so something like a trifluoromethyl group will be very strongly deactivating because that carbon has so little electron density it's going to withdraw. And then we have quaternary ammoniums. Those will also fall under the category of strong deactivators. So with this, nitro groups, trihalogenated substances at that carbon, so trihalomethyl groups, that's CX3. Remember, X is our halogens, and then quaternary ammoniums. Because again, that has that positive charge there. We do not want to put a positive charge right next to another positive charge. These will deactivate because those will be withdrawing electron density. And we're going to see that both MDs and SDs are metadirectors. There's our, most things are orthoparadirectors, but moderate deactivators, I almost call them meta deactivators, maybe we should, and strong deactivators are both metadirectors. And in our next video, because I know this one was a little long, we're going to take a look at what these look like in reactions.